Thank you all for coming and listening to us. My name is Tino. I work on Google BigQuery. And we're going to talk about some interesting advanced topics, namely real-time architectures. Real-time tends to be fairly difficult, but it doesn't have to be. And so we worked really hard to make that as easy as possible for you. So we'll go into that a little bit detail further on. But first, let's hear it from a customer who has gone through his journey throughout the last 4 or 5 years with us. Please welcome Yuki, who is the CTO of Plaid. Yuki, please.
Thanks, Tino. Thank you for taking time for our session. Truth be told, this is my second English presentation in my life. So I apologize in advance. If you cannot understand or want to know more about detail my part, please find me and talk to me after the session. I teach you Japanese and talk in Japanese. I'm Yuki Makino, CTO of Plaid. I'm working in Plaid, and I'm in charge of real-time analytics data engine for about 4 years, and since before the release of our service, Carte. Today, I'll show you our architecture history and BigQuery usage pattern in my part. Okay. Plaid is a fast-growing startup company in Japan. We provide real-time analytics service named Carte. Carte has 3 characteristics comparing with other data services: real-time, large scale, and global and multi-tenant. Sorry. Carte is a real-time analytics tool, so it handles data in real time. And it has more than 500 enterprise-scale clients. And so data volume we handling is very large. And clients are isolated by data set to share the data collected by Carte to clients. And some Japanese clients prohibit to put data in foreign countries, so we distribute our data to multiple global regions in BigQuery. Okay. Carte is not only data visualization tool, but also action tool. So it processes data and returns actions within 1 second. So it's really real-time service within 1 second. It processes 65,000 events per second, 3 billion events per day, and it inserts 1 petabyte streaming data by streaming insert per month. And currently, we store more than 2 petabyte data in BigQuery, and more than 60 petabyte analysis per month. And we contracted flat rate plan with 6,000 slots, 4,000 for US and 2,000 for Japan. Okay, and as you can see, this represents that we use BigQuery very heavily, and this is why this is the reason why I share our experience today. Okay. In order to understand architecture easily, I'd like to have a brief introduction of Carte. Carte is a website real-time custom analytics and action tool. We call it Customer Experience Platform. It is for managing customer experience in website to know real-time customer state and to do appropriate action which are suitable to each user. I'd like to show more technical concept of the system. Current system concept is a real-time reactive system. Firstly, an end user sends event to our system, and currently analyze the current user state based on 4 events the user has sent since the first visit. Based on the calculated state, it returns appropriate actions as reactions to the latest event the user sent. And also, our clients can see real-time user state and configure actions in the application in real time. Our clients set actions to segmented to users, then the action for some segments are started to fire instantly. Right? We started to use BigQuery about 4 years ago, soon after our first release. At that time, we inserted event log data by streaming insert simply. We use BigQuery just for log analysis at this moment. And next phase, we started to use BigQuery in the production application directory to show analyze data to our client. We also started to insert analyze user state data in BigQuery in order to aggregate user state in the application. Right. This is current architecture. We add new data management functions so that our clients can import and export data in BigQuery with data flow. And it can also export data to Spanner and Bigtable to serve data in latency-sensitive layer. BigQuery actually center of our data ecosystem, not only for us, but only for our clients. We use BigQuery in various ways to realize the real-time analytics service. All right, so today I'd like to show 5 real-time BigQuery usage patterns we use in production system. The first pattern is complex query and cache pattern. This pattern is in front of client application. This pattern can be used when you want to make a real-time consuming complex query in production system. In normal way, when you want to analyze data stored in data lake or warehouse through production application, you put ETL layer and fetch data ETL to database. Previously, we used another ETL database to fetch analyze data, but it's complex and not flexible and not real time. When we try to change access pattern, we had to change the ETL process and the application code to fetch the data. So we lock it in memory cache layer in front of BigQuery and access it with SQL transparently. If you want to change the access pattern, you just edit SQL text the application use. It's very flexible. In our case, we use hash value of SQL text as a key of cache entries. If the hash entries do not exist in cache table, then it runs the query actually in BigQuery and create new cache entries. In your case, however, in this pattern, cache missed query takes some time. So if you want to shorten the fast query latency, optionally you can create cache asynchronously in background in advance, and then you can reduce the latency pop. And this is actual production screen. Actually, we use the first pattern to show this view. You can see real-time data in application. It's quick enough like common application. Okay. The next pattern is ETL on simple query pattern. This pattern is also used in front of client application. When you analyze data more interactively with BigQuery, this pattern is useful. BigQuery is powerful, so we store for log everything to BigQuery as data lake with schemaless and JSON string. BigQuery is enough fast even for these kind of raw data. But if you want to do a little heavy task, such as parsing large JSON, join, and multiple step aggregation, it may take more than 10 seconds. If you want to analyze this schemaless data more interactively, BigQuery ELT saving query is suitable. Saving query is very useful and fast and simple. Saving query saves query results as a new table. You don't need any additional system to do ETL and ELT. To see real-time data, periodically it extracts key and values from raw JSON, calculate aggregate values, and merge into the simple summary table. Okay. For example, with saving query, it passes the JSON log data and aggregates values grouped by user ID, and creates a row having segments and stats of each user. And from production system, the application runs simple queries such as intersection. The query latency or BigQuery for simple query is very low. Look like this, super fast. This is implemented only by ELT, the BigQuery table, simply. The next pattern is a frequent update large row pattern. This pattern is used in streaming insert of user data. When you query for the latest data, raw data, this pattern is useful. If the average row size and cardinality are not so large, you just insert all rows and query the latest row by using string arg or row number. But if the average row size and the cardinality are large, the cost, including streaming insert cost, storage cost, scan cost, becomes high. So we put buffer queue to reduce cardinality in front of streaming insert. Buffer queue stores data to be inserted in concurrent short time. Let's say 3 minutes. It stores it in 3 minutes since the first entry. And if a row having the same key counts, it just overrides the original entry's value. After the 3 minutes since the first entry, the entry is inserted to BigQuery with streaming insert. By using this buffer queue, it prevents to write unnecessary old rows to BigQuery. Buffer queue can be implemented by data flow or in-memory queue. Actually, we use in-memory Redis queue. Okay. In your case, we use this pattern for analyze user state data. The average of raw data size is about 200 kilobytes, and we set buffering time 5 minutes. It inserts 800 terabytes per month with this pattern. If we didn't apply this pattern, the data size would become 10 times more. So by using this pattern, we reduce the cost by 90%. The fourth pattern is optimized for low latency serving pattern. This pattern is used for latency sensitive layer. When you want to use data in BigQuery in latency sensitive system, you can use this pattern. Data flow can easily export data in BigQuery to other GCP data store service, including Spanner, Bigtable, GCS, and Redis. In our case, we export the data to Spanner and Bigtable to use in the latency sensitive layer. For example, we export such as membership information and recommended information stored in BigQuery to graph user state or make recommendation action. Spanner and Bigtable are key value-based data stores, so if a scope of entries to be fetched is small, the latency becomes very low. So if you want to use data in low latency system, it is reasonable to export data to these key value-based data store. And the last pattern is the direct join pattern. This pattern used in client data management layer. If your customer has own real-time data in BigQuery, you can directly join it your data set over a project. If your data is real-time and the customer's data is real-time, then joined data is also real-time. You can control access right in dataset level, so you should separate data by each customer to share. Once datasets are shared, then you can touch the shared dataset within SQL directly. Don't need any operation cost for import and export. If you use BigQuery flat rate, zero additional cost is required with data linkage and analysis. If you care sensitive data, VPC service control helps you. It can control access rights of data in GCP services in fine-grained level. Okay. Direct join pattern can do if the target dataset are located in the same region. In our case, on the other hand, some BigQuery Tokyo region users, including government, financial services, and banking services, is restricted to store data in Japan by the company policy and never export sensitive data to foreign country. In this case, we copy data from global region to restricted region, or insert with streaming insert to restricted region in advance. We contract US region and Tokyo region flat rate. We analyze data in US region basically, and when we want to analyze with sensitive data, we analyze in Tokyo region. Okay, I just shared 5 real-time patterns we use in production system. This is the last slide in my part. BigQuery is the core of our analytics architecture, as I showed. And it is not only large-scale and high-throughput data engine, but also can be important role in real-time system. And it is suitable for global scale service like Carte. Now it is the center of data ecosystem for us and also for our customers. That's it. Thank you.
Thank you, Yuki. Thanks for Team Plaid coming out all the way from Tokyo to share their story and share what they've done over the past years. But Plaid started out with Google and BigQuery 4 years ago, and they didn't start with, as you saw, they didn't start with the massive architecture that they have today. They started slow, and that's really the message that I want to tell you guys is that you don't have to re-platform, you don't have to re-architect things. Real-time doesn't have to be hard. You can start with a very basic architecture. If you're building a brand new architecture, it doesn't have to be difficult. And if you have an existing environment, you can simply just put this on top of that, right? So very minimal disruption of your existing environment. And this is actually probably top 3 architecture for real-time analytics at Google. That's it, right? Going from your application using BigQuery's streaming API, which is awesome, straight into BigQuery. And your data is available as in real time, right? And a lot of our customers do just that. And that's perfectly acceptable. But you can, our services work together well. And everything is extendable. So you can continue to kind of expand if you wish to do so. So for example, if you have an IoT use cases or mobile, maybe you have gaming, logs, and so on and so forth, maybe it makes sense for you to keep some intermediate state that passes information back to the end device. In which case, you might want to use a high-performance, low-latency database like Bigtable or Firestore. We actually built integration with both of those. You can actually query Bigtable data directly from BigQuery without even moving it into BigQuery. And on top of that, as you saw with Plaid, you can start using BigQuery as an ETL or ELT tool itself, right? You can move data from left to right, cleanse it, enrich it in BigQuery itself. The next stage, potentially, if you so desire, is to start thinking about a true real-time architecture. Right? So you can start thinking about putting Cloud PubSub or Confluent Kafka in your architecture, kind of like as a shock absorber. And then you can use our excellent service, Google Cloud Dataflow, or you can use Hadoop or Spark specifically on Dataproc for real-time data processing, to enrich data, to cleanse it, to create reports in real time, moving that data into BigQuery using our streaming API again, and potentially even cleansing it further. So things are getting more interesting. And as you develop, there's more and more options, right? You can take your data from left to right. And finally, if you start to really want to productize your architecture, we have services that allow you to control your security, privacy, access controls, network, and so on and so forth, and including orchestration. So all of these things are kind of fairly flexible, right? But let's talk about one specific pattern here, and that is once your data is in BigQuery storage, what can you do with it? Especially, what can you do with it that doesn't have to do with the things that BigQuery provides, right? So we've built standard SQL with lots and lots of extensions that allow you to express your logic just in plain SQL. We built UDFs, user-defined functions, that allow you to go a little bit beyond that. We also introduced declarative BigQuery machine learning in SQL and geospatial capability in the last year. And so all these things kind of allow you to do a lot of things on BigQuery storage. But as long as you are bound by these processing terms. But of course, you're going to say, Tino, how come I have lots of other things I want to do with my data, but it's already in BigQuery storage. What are my options? Right? So whether you're using languages like Python, Java, or Go, maybe you have a Jupyter notebook or Zeppelin. Maybe you're using different libraries like Pandas or Keras, or different distributed processing frameworks like Spark or Flink. What are your options, right? Your data's already in your data warehouse. What can you do with it? Well, there's a couple of them, right? One is maybe your data warehouse allows you to put agents into the data warehouse. So you can run third-party code in there. Or maybe you can move data, like kind of read data from storage directly, so trickling data out. Or maybe you can bulk export data, which is kind of this uncontrollable monsoon of data. So to recap, the options are you can trickle data out just by using a list API, right? You're paginating over data, which can be about 20 megabytes a second in BigQuery. So it's real time, but it's very slow. It's not parallelizable. You can bulk export, which is decisively not real time. It requires a middleman like Google Cloud Storage. It's probably going to take you, dozens of minutes to hours to move lots of data out of BigQuery. So maybe it's not suitable for some of the more real-time use cases. And finally, we're not going to let you have third-party agents running in BigQuery. It's just a security no-no, right? It's just something that we can't do, right? So no good options, right? And ultimately, when you think about it, your data warehouse storage typically is kind of locked out, right? Your storage is locked away behind a castle with a huge wall and a moat around it. Yeah, you kind of don't have a lot of options. And I guess a quick segue, I was going to use a real image for this slide, but I couldn't get rights to it. So I went on Twitter last week, and I asked folks to draw a picture. And this is the winner of the contest. And the good news for me is that this happens to be my boss's wife. So it's good. Hopefully I get a promotion out of it. But there is one workaround that we see in the wild out there, right? If you have data in your BigQuery storage or other data warehouses, You could potentially keep a copy of that data, quote-unquote data lake storage. So it could be GCS, it could be HDFS. You could use Parquet files or org files. But this is a little complex, right? It allows you to leverage these non-BigQuery processing systems on top of your storage, but it's twice the complexity, twice the cost, twice the operational headache. We feel like we can do better. So I'm going to pose the question is, what if you could treat your data warehouse storage like a data lake, like storage, really? What would that look like? Well, I have an answer for you. And we launched something called the BigQuery Storage API. Right? This solves this exact problem. Let's talk about that some more. So BigQuery Storage essentially allows you to read data. BigQuery Storage API allows you to read data from BigQuery storage at low latency, right? So 1 second to first byte. It's highly parallelizable. So, as if you have something that's reading from that's distributed, that's reading from BigQuery Storage API, you will have some really serious throughput. We measure, multiple dozens of gigabits per second. And it's also very flexible. So you can take advantage of BigQuery's columnar formats and so on and so forth, right? So it's really useful, and it allows you to do that non-BigQuery compute native processing on top of BigQuery storage. And with that, I'd like to welcome Seth, who is a developer advocate engineer. He's going to talk a little bit more about this and give us a demo as well. Seth.
Thank you, Tino. There we go. Thanks, Tino. So those of you coming from other data warehouse technologies, like when you're dealing with your data warehouse storage, you're dealing with a lot of complexity. Like you have to deal with file system layouts, how you map storage to nodes, all sorts of kind of indexing and vacuum strategies. There's all this kind of management overhead that goes with maintaining your data warehouse. And when we built BigQuery, we thought maybe the thing to do is to provide an expert to every user. And we do that by managing your storage on your behalf. You don't have to worry about all these low-level issues, and you can focus on deriving insights from your data as quickly as possible. So let's talk about what it actually means to be BigQuery storage. Our primary abstraction is the notion of a table. And when we present a table to you, we focus your interest on like the things that matter for your use cases. Like you define schemas. So you set us you tell us what kind of columns are available in your table, what kind of typing information. We have a lot of type functionality, so you can do things as simple as strings, fixed precision numbers, floating point, bytes, geography types. We also support complex data types like structures and arrays. You also provide information that's useful for the consumers of your tables. So you provide descriptive metadata about the tables themselves, any information you want to relay to users of the tables about what's actually contained in these columns. Like, how should I use this data? There's access control policies, data lifecycle policies, so you can decide, like, when should data age out of this table? Am I setting up for a world where I retain all information indefinitely, or do I want to maintain a sliding 90-day, 365-day window that tells me, as data ages out, remove it from the table automatically? I don't want to think about it. The final thing you do is you provide hints to us through the notion of partitioning and clustering that basically tell us, these are the kinds of access patterns I'm going to use with this data, and we use that information to speed up access for you. When we look at a table, we see a much different view. So we take everything from that first slide, and that's basically the user metadata. And then we're doing all the tracking for everything else that happens in the system. So BigQuery supports what's known as a snapshot isolation model. So at a given point of time, we know what data is available in the table and what's not. And so we maintain all the information about this data arrival, data leaving. We also have to deal with all the replication on your behalf. So you don't ever have to think about where's my data, is it fully replicated? That's all handled for you. As I said earlier, the lifecycle information. So we know at a granular level what storage should be arriving and leaving the table. Internally, we also have a bunch of other stats for understanding operations that mutate storage. So in addition to that metadata layer, where do we actually put the contents of your table? Like where is the data for your table itself held? We've talked about this in some blog posts previously. So we use a columnar format for your data called capacitor. And what that does is it provides us very fast ways to access your data such that it supports kind of analytic workloads. So as opposed to like a transactional system where you're doing a lot of frequent mutations for individual entities, in an analytic data warehouse, you're scanning a lot of rows at any given time. We also, so as this diagram kind of shows, in addition to grouping data based on transactional operations, we also group on a higher level abstraction of the partitioning information. And so what that effectively means is whenever we want to read a table, we end up with a set of columnar files that we need to operate on. Our query engine basically opens all these up simultaneously. And so what we've done is we've tried to figure out a way so that you can do very similar things. Essentially, what we want to present is the ability for you to act as a query engine. So on the left, as you see, we have you've selected some set of, you've selected a table or partition, and you want to read that into your external application. We deliver that through a set of streams, and then we do decoding on the client side. So in comparison, let's talk about what you could do today. As Tino mentioned, we have the table data list mechanism, which is a paginated cursor method. So it's a REST API, which means you're doing individual discrete HTTP requests and responses for each page of data. You have all this auth flow to get through, and the data is presented to you in a JSON format, so it's not particularly efficient at scale. By contrast, the storage API does a couple different things to handle this. On the network layer, we use gRPC and a streaming RPC protocol to ensure that the latency for just moving data back and forth is as low as possible. And we use a lot of flow control to make sure that data is continuously arriving. We use a binary serialization format. So those of you that are familiar with formats like Apache Avro, you will be reading Avro out of these streams. We're also looking at other delivery formats, so feel free to catch me after the talk and tell me like your favorite format and why, and we can look at what we want to do there. We also use this abstract concept of a stream to deliver data, and that's our unit of parallelism. So streams make it easy to build consumer applications based on the notion of your architecture rather than our architecture. We didn't want to ship a bunch of complexity around understanding our low-level storage interfaces, and so we built this abstraction for you. So when you set up a session, you basically tell us basic information about what kind of data you want to read, properties of the table, how you want to access it, and importantly, the parallelism you want to read it at. Even a single stream is generally more performant than the new method simply due to the technology changes. As you are able to scale up across multiple nodes, you can establish additional streams, and your throughput goes up as well. And you can keep doing this. The basic bounds you have are how much bandwidth you have available, do you have the compute capacity to do the decoding, and what is the underlying parallelism of the table you're accessing. So a very small table may only be represented by a single file, so you're not able to use more than a single stream to access it. By contrast, as Yuki mentioned, like they may have terabytes to petabytes of data. That could be represented by hundreds or thousands of columnar files. And so your parallelism factor scales as the amount of data scales. So the other thing to keep in mind is we don't make you reason about which files are going into which streams. We do a dynamic dispatch so that essentially all you have to worry about is the stream, and we will make sure that data is delivered to the streams. And We allocate things in a safe way so you don't have to worry about duplication due to the network transport. However, you're dealing with distributed systems. Distributed systems fail. They just do. So how do you deal with that when accessing your storage through this API? So we essentially present 3 levels of recovery and error control. So each of those streams has an offset mechanism. So if you have a bad read, you can basically restart at the last point you had a good read and continue on. If, for example here, if like your receiving node failed and you need to restart the entire stream, that's perfectly legitimate as well. And say you had a much more catastrophic failure, you can restart the entire stream, and we will deliver the data in the same order we did in the original session. One thing to keep in mind, though, many applications are inherently single node. A lot of people have tools that just run on a local machine. As long as you have sufficient capacity on that machine, it's perfectly OK to fan in multiple streams onto that worker. One thing to keep in mind, there is no ordering guarantees for each element of the stream. So you can't say stream 1 is going to get A through M, et cetera. So when we think about the storage API, we want to give you the same capabilities we give our query engine, which means projection and filtering. If you only want 2 or 3 columns out of a very wide schema, we will only deliver those columns. That speeds you up because, obviously, we're not sending that over the network, and we're able to leverage our columnar format, so it's very fast for us to do this. Similarly, you can establish row filters to say, I would like to throw away any data on the server side before it even comes across the network so that my consuming application doesn't have to even look at it. And you can do that as well. So as I mentioned, so we have a snapshot isolation mechanism. This is sometimes called time travel in our system. So we also give you the ability to say, I would like to read this table as of midnight yesterday, or 3 hours ago. Cases where you might want to do this, if you just recently did like a big DML update and changed a bunch of your data and went, wait, what was the state of that table before I did that? You can walk before that event. Similarly, if you're doing like simultaneous reads of a bunch of tables and you want a coherent point in time for all 3 of them or however many you're reading, you can set the snapshot time for all of them to be identical. So if I could switch to the demo real quick. So one thing to keep in mind is I'm terrible at visual demos. So what we'll be doing today is I'm going to demonstrate like comparing the use of the existing API to the new API. And we're going to use some data from the public data program, the public data sets program. And in this case, what we're going to be working with is something called the sample commit stable. So it's basically a subset of all the commit history in GitHub open source projects restricted to some subset of the available projects. And we do that because the raw data is 753 gigabytes, and we can demo it, but it will be a much longer demo session. This one, by contrast, is only about 2.5 gigs, a couple 100,000 rows. And so let's look at, essentially, I have 3 nodes here, the GC VMs, absolutely vanilla that I've just put a variant of Debian on. So to set the stage, top box is the existing cursor method. It's going to move, but it's not going to move particularly fast. So if we switch to the storage API in a single stream, we're doing a little better. we're certainly going to arrive at the end before the first one. So let me stop that, and let's parallelize it some more. So my beautiful bar chart, each color is the data being delivered to a specific stream. So with a parallelism factor of 4, we're moving a little faster. We can stop that, make it bigger, add more streams. And unfortunately, text demos aren't the greatest for visuals, but low-level storage APIs don't inherently make for great visual demos, I'm sorry. So let's do one more thing. So in addition to that, we talked about the fact that you can do column projections. So if we say we're only interested in the actual commit hash and the author's email address, the addresses are anonymized, so we lose the identifier, but we keep the domain suffix in this data set. A little faster. And last thing we can do is say, so this bar chart doesn't look very pretty because we're filtering almost all the data out. As you can see, we apparently, this is the equivalent of a count star query on the table where we say where the domain suffix is like that filter. So we have apparently 6,000 commits in the GitHub data. And as you can see, we're still waiting on table data to make its way to the end of the table. That's all I had for the demo. Could we switch back to the screen? Now I'd like to, yeah. Tino, I'll turn it back over to you, and I'll go sit down over here.
Yes. Wow, fantastic. Thank you so much, Seth. So yes, I think between hand drawings of castles and text demos, we've really raised the bar here. But the point stands. It's a really, really fast API. And as a product manager, I like this slide a lot. And hopefully as a customer, as a user of BigQuery Storage API, you like it as well. So it's in beta. It's out now. Go start using it. There are still some things that we want to do to get it to GA, but it's already out there. It's already highly useful. So how do you use it? Well, one is if you have Dataproc running or Hadoop or Spark, we have released and are continuing to release a number of connectors. So for example, Hive, MapReduce, Spark SQL, or you can actually even can just create a pandas data frame that is powered by BigQuery Storage. This is really powerful because, for one, the patterns I've described before, you no longer have to do that. And two is you don't need to sample your data and reduce it on your BigQuery Storage before loading into pandas. You simply have a data frame that runs on top of BigQuery Storage. It's great. The next one is if you're using Dataflow, which is an incredibly powerful unified batch and stream processing engine, you can read data out of BigQuery Storage, do some enrichment from third-party sources, maybe PubSub, and put it back into BigQuery Storage using our real-time streaming API. So now you have a real-time ETL processing system. So the Dataflow connector's out there. You can start using it today. Finally, ODBC and JDBC, right? That's some good examples of tools that could be potentially be benefiting from this. We've already updated the JDBC driver, and ODBC is coming very shortly, right? So you just get a quantum leap of performance if you're using any third-party tool that relies on mass. Or you're programmatically connecting to BigQuery using ODBC or JDBC. And finally, as Seth pointed out, it's an API, so you can start using it. Just go and start building code on top of it. And we'll have client libraries and all the good stuff that you're used to relying on. And we'll continue to expand on this ecosystem. So as Seth pointed out, if you have some requirements, if you're interested in other things that could work on top of BigQuery Storage API, please let us know. We're really excited to build all that. And so I kind of give you a whirlwind of the different patterns that are possible here, and you saw some of them live with Plaid. But this is just a sampling, right? This is not everything that we can give you. But I'm really excited to tell you that that one pattern of your data being in BigQuery Storage is now, we feel like, is very unique and it's very powerful. And we're looking forward to hearing how our customers are using this. We already have a couple of users of this API, mixed panel Taplytics, which are kind of similar to Plaid, their marketing analytics providers. And they're using this at scale, and it's kind of opened up a new way of doing things. It's much simpler than the old ways. It allows a cleaner architecture in general.